Hi everyone, welcome back to the fifth video in this series of Snow Day lectures. What we're going to talk about now is the regiochemistry of epoxide openings under acidic conditions. And so what I mean by this is if we have a similar epoxide that we talked about previously under basic conditions that has different substitution on both sides of the epoxide, where is our nucleophile preferentially going to add? And so, just as a refresher, on this side we have a primary electrophile, whereas on this side we have a tertiary electrophile. And so, unlike under basic or neutral conditions, where we are going to treat this really as just an SN2 type reaction, and we're going to go ahead and crack open the less substituted side, under acidic conditions, the regioselectivity winds up being quite different. So specifically, the regioselectivity of an acidic epoxide opening is going to favor the attack on the on the more substituted side. So let's write that down. So regiochemistry regioselectivity, which is the selectivity of regiochemistry, will favor the nucleophilic attack of the less substituted side. Excuse me, more substituted side. More substituted side. So in this case, what I'd like to do is highlight the difference between basic and acidic conditions by taking this same electrophile here that has this both primary and tertiary position, and we're going to treat this under a series of similar yet different conditions that are going to wind up giving us a different structural isomer of the product. And so over here, what I'd like to think about is let's react this under acidic conditions. And so I'm going to add some sort of acid. And so again, we'll stick with H2SO4 just because we can. And I'm going to do this under a solvent of ethanol. The solvent of ethanol is going to function both as what dissolves everything in solution, and it's going to act as our nucleophile to crack open this ring. So under acidic conditions, remember that we are going to go ahead and attack the more substituted positions. We're going to favor the tertiary over the primary. So what this will look like then is we'll have our ethanol nucleophile come in on your right side here, crack open the ring, and give us our alcohol on this position that ends up with a primary alcohol here. So if we want the other possible isomer of this, what we can do is we can run this reaction under basic conditions. And so what that would look like is in our first step, we could treat this with sodium ethoxide. NaOET. And then in a second step, add our proton in the end so that we have a neutral product. And so you can just think about this in a little bit of HCl maybe. So what will happen is under basic or neutral conditions, and sodium ethoxide is a relatively strong base, so we can consider this quite basic. What we'll do is we'll preferentially attack the less substituted position, in this case the primary position. And what that will give us is the opposite connectivity of our alcohol product. So instead of being a primary alcohol because we've cracked open the ring at the tertiary position, we are now a tertiary alcohol because we've cracked open this ring at this primary position. And so by controlling the different types of conditions that we run these reactions in, we're really able to get really nice control over the type of products that we wind up producing. What I'd like you to think about is that why are we seeing this difference in selectivity? And so, while I'm moving the camera, I'll continue to talk. From the perspective of an SN2 reaction, attacking the less substituted side makes sense. Sterics winds up playing a role, and being able to access the LUMO winds up being very important. Under acidic conditions, not quite so much so. This is still an SN2 type reaction, but what we wind up seeing is that really the selectivity is not very SN2 in nature. And the reason that this happens is because we're actually starting to form a little bit of carbocationic character in our epoxide before the nucleophile attacks, almost like an SN1 reaction. So let me show you. So let's say we've got our epoxide here, and we're adding some sort of acid. So we'll just say H+ for now. The epoxide is going to use its lone pair of electrons on oxygen to reach out and grab that proton. We'll create our oxonium species here that really supercharges the electrophilicity of this ring. And something actually kind of interesting winds up happening here. Whenever we've protonated this oxygen, we've turned the leaving group from a decent leaving group, because of the ring strain, into an absolutely earth-shatteringly good leaving group. It really, really wants to go. And it wants to go so much, the fact that the bond actually starts to break before you even have the nucleophile come to approach. So in reality, this winds up really looking like something like this. Where we are starting to break one of these carbon-oxygen bonds in order to really give some relief to this positive formal charge on our oxygen. And so really this molecule has an interesting question to answer, is that, okay, if I'm going to start breaking a bond, which one of these bonds would be most energetically stable for me to break? Another way to put this is, if we're going to form something with partial positive charge, where do we want to put that partial positive charge? Probably where the carbocation would be most stable. And so the epoxide makes that decision here. It realizes that if I start to break this bond at a greater rate than I start to break this one here, my partial positive charge is going to be on a tertiary position. And remember, tertiary carbocations are more stable than primary carbocations. And so even though this isn't a true blue carbocation here, what you wind up having is partial carbocationic character there. And so the greater the substitution, or the more stable your carbon is going to be with that partial positive charge, is the more likely that they are going to go ahead and attack that position. And so when your nucleophile then comes in, we'll say that this is still ethanol. Even though this side is more sterically encumbered, what it's going to do is it's preferentially going to be drawn to this side by electrostatics. It is a partial positive charge, and so as a nucleophile, oxygen is going to look for a partial positive charge to share its electrons with. And in doing so, this is what gives us the opposite regiochemistry that we wind up seeing on an epoxide opening under basic or neutral conditions. And so, in this case, just a reminder, this would crack open, giving us our alcohol here. Subsequent deprotonation would then give us our neutral alcohol in the end. Okay, so where we are going to go next time is we're going to start thinking about how we make alkynes, and then more specifically, how can we use elimination to give us a product that doesn't necessarily follow Zaitseau's rule. Okay? See you for the next and maybe final video. We'll see how long this takes.